Welcome to The Explainer. Today we're going to break down a really clever algorithm that quietly powers so many services you use every single day. It's the secret to finding that one needle of similarity in a truly massive digital haystack.
Okay, so let's start with a problem that is just mind-bogglingly huge. Think about companies like Google, Netflix, or Spotify. They have trillions of data points, documents, songs, movies. How on earth do you find ones that are similar to each other? You can't just look at them all. It's an impossible task.
I mean, the obvious way to do it, right, is just brute force. You take one item and you compare it to every single other item. But if you actually tried to do that with, say, every document on the internet, you would literally never finish. The scale of the problem makes that direct approach a complete non-starter. So instead of using a computational sledgehammer, computer scientists came up with this incredibly elegant solution called Locality-Sensitive Hashing, or LSH for short. And it's less of a tool and, honestly, more of a clever magic trick.
Now here's the part that's kind of wild, because it flips the whole idea of hashing on its head. See, normal hashing, the kind you use for security, is designed to avoid two different items getting the same hash. But LSH? It does the exact opposite. It's a special kind of hashing that is sensitive to how similar things are, and it actually wants similar items to collide.
And this is that magic trick in action. If you feed two similar documents into an LSH function, they've got a really high chance of landing in the same conceptual bucket. But two very different documents? Nope, they'll almost certainly end up in different buckets. This is huge, because it automatically groups similar stuff together. Now we only have to search inside a few of these tiny buckets instead of the entire haystack.
But for any of this to work, we have to get really specific. You can't just tell a computer to find similar things. We have to define mathematically what similar even means in the first place.
And a couple of really popular ways to do this are Jaccard similarity and cosine similarity. You can think of Jaccard as being great for comparing simple sets, like what movies did two different people watch. Cosine, on the other hand, is much better for more complex things, like documents or images that have been turned into these long strings of numbers called vectors.
Jaccard similarity is actually super intuitive. You just take the number of items that two sets have in common and you divide it by the total number of unique items between both of them. So, for example, if two shopping carts have 4 items in common and a total of 8 unique items between them, their Jaccard similarity is 0.5 or 50%. Simple, right? And really effective.
Cosine similarity is a little more abstract, but it is incredibly powerful. So just imagine every document is an arrow, a vector, pointing in a specific direction in this massive, high-dimensional space. Cosine similarity doesn't really care about how long the arrows are. It only cares about the angle between them. It's basically just asking, are these two things pointing in roughly the same direction? If the angle is small, they're very similar.
Okay, so how do we actually build an LSH function that uses something like cosine similarity? Well, one of the most popular ways is a method called SimHash. Imagine all our data points are just floating around in space. SimHash works by just drawing a random line, or what's called a hyperplane in more dimensions, right through the middle of everything. If a data point falls on one side of that line, we give it a hash of 0. If it's on the other side, we give it a 1.
Now think about this for a second. If two of our data points are really close together, it's actually extremely unlikely that our random line is going to slice right between them. They'll probably land on the same side and get the same hash, either both zeros or both ones. And that is the sensitivity to similarity we've been looking for.
But, a single hash like that isn't quite reliable enough for the massive, messy datasets we see in the real world. So how do we take this cool little trick and turn it into a truly robust technique?
The challenge here is that a single hash gives us a slight tendency, a probability, that similar items will collide. What we need is a way to amplify that. We need to widen the gap so that similar items are almost guaranteed to be found and dissimilar ones are almost guaranteed to be ignored.
And we do that by tuning two parameters, k and l, that kind of act like control knobs for the whole algorithm. First, we'll run, say, k different hash functions, and we'll stick the results together to make one long signature. This makes our test for similarity much stricter. Then, we repeat that entire process l times over, creating a whole bunch of independent hash tables. This just increases our odds of finding a match.
When you combine these k and l knobs, you get this really powerful effect. The result is something known as an S-curve. It creates a sharp cliff. For items that are below a certain similarity score, the chance of them colliding gets pushed down to almost 0. But for items above that score, the probability gets pushed up to nearly 100%.
So it's no longer just a gentle slope. It becomes a really decisive separator.
Okay, so where can you actually see this thing in action? The answer is pretty much everywhere you look online. It's one of those hidden technologies that shapes your entire digital world. LSH really is the secret sauce behind a huge range of applications. It's what search engines use to find and get rid of duplicate web pages. It's used by services like Turnitin to spot plagiarism. And of course, it's what powers the recommendation engines on Netflix and Spotify. You know when Spotify just nails that song suggestion? Yep, LSH is probably working its magic behind the scenes.
Probably one of the most classic, almost legendary examples is something called market basket analysis. Retailers, obviously, want to know which products people tend to buy together. And decades ago, analysts, using these kinds of techniques, stumbled upon a correlation that was, well, pretty surprising.
By calculating the Jaccard similarity across millions of shopping trips, they found that people buying diapers were unusually likely to also buy beer. I mean, as this chart shows, the similarity score for that pair was way higher than for other common items. And that single insight allowed stores to place beer and diapers closer together, which boosted sales of both.
And this really brings us to the main takeaway here. LSH isn't about finding the single 100% perfect match. It's about finding a good enough match and doing it incredibly fast. It makes a trade. It gives up a tiny, tiny bit of accuracy for a monumental gain in speed. And that trade is what turns impossible problems into solvable ones.
So this leaves us with a final thought. With clever algorithms like LSH that can sift through these ever-growing oceans of data, what other surprising patterns about the products we buy, the media we consume, and even about ourselves are just waiting out there, hiding in plain sight, ready to be discovered next?